Welcome to Driven. I'm your host, Paul Perrone. We're going to learn and talk about AI, robotics, autonomous vehicles, and so much more. Check us out at driven.show on the web and give us a thumbs up or subscribe here if you like the show. So kick back or buckle up and become driven. Okay, welcome to episode 22 of Driven. This episode is about sensor fusion. So this is about how different objects detected from different or perhaps the same sensor are resolved to be the same object or perhaps a different object. How do we figure that out? This episode is all about that, sensor fusion. We're building off of the last informational episode, episode 20, where we talked about LiDAR perception. And so this was an episode that discussed how LiDAR, a very popular sensor in the autonomous vehicle space, can be used to detect objects in the world using laser light to bounce off of objects and detect shapes and other characteristics about the object and get the distance to that object to where it is in the physical world. So we saw a little bit about how we detect objects in sort of 3D space and a little bit over time with successive scans of this LiDAR to view the world. So check out that episode if you haven't quite learned about how objects are detected to begin with, because that really sets the premise for what this episode's all about. But nevertheless, if you want to just start here, you can do that as well. You can assume that there are sensors that detect physical objects in the world. And in this case, this is going to be with our autonomous vehicles, LiDAR, radar, camera, might be ultrasonic sensors, different types of sensors that are on the vehicle. And as I mentioned in episode, 20? We showed how LiDAR could perceive objects in the physical world and detect them. So assume going into this episode that we've detected one or more physical objects out in the world. These may be cars, these may be people, cyclists, dogs, cats, buildings, what have you, right? So we've detected something, or we've detected many somethings, of course, in the physical world as the car is driving down the road and trying to get to its end destination. Some of these objects that are detected from LiDAR sensors, as we discussed in episode 20. So we get the width of these objects, we might get the height, we certainly get the distance to them and where they are relative to the vehicle, their relative orientation, perhaps how fast they're moving, and other characteristics that we can gather from LiDAR perception. Now, there are other types of objects that can be detected from different types of sensors. In the case of radar, we get what's called targets. These are just other objects. The radar can typically tell you where something is in terms of its distance relative to the vehicle and its relative azimuth to the vehicle's current heading. So you can get information about the distance to the object, its relative angle, and also its speed from radar detected objects. So another class of objects that can be detected, as well as cameras are used very often on vehicles as well based on the image and machine vision processing and other algorithms that are applied to the camera image, being able to extract from it objects that may be in that image, such as cars and people and what have you, and indicate that something's out there. Certainly to be aware of. And if you have stereo vision where you have two different cameras and a fixed baseline between the camera lenses, you can kind of project the distance to that object, even from camera-based object detection. But suffice it to say that you'll have a pool of objects that are collected from camera-based perception as well. And then there are other sources. You can have a networked vehicle where other vehicles and other sensors in the physical environment are detecting objects and can communicate to the vehicle via what's called V2I or V2V or V2C, vehicle to infrastructure, vehicle to vehicle, or vehicle to cloud type communication interfaces to communicate to the vehicle what other objects may be out there in the world, dynamically or statically. You can upload data from a database that may tell you here's some fixed physical objects in the physical world that you should be aware of. And of course, other sources such as ultrasonics, thermal imaging sensors, different types of sensors that you may have on vehicles that can tell you where things are in proximity to the vehicle. So now you have a collection of objects, depending on the sensor, depending on certain characteristics of the objects, you might be able to gather certain attributes and information about the object. As I've mentioned, you can often from LiDAR infer the width of the object, at least when you first see it, perhaps the height, the speed of the object from LiDAR or radar, perhaps with successive scans of LiDAR or just using the raw radar target information, you can get the speed of the object and the direction that it's headed as well. So these are certainly key attributes of an object so that you know, not only know how far it is, but how big it is and what its speed is and what its direction is traveling. Obviously, vehicles will be traveling faster than pedestrians. That's one clear indication very often that something you might think is a pedestrian, if you think it's traveling 50 miles an hour, it's probably not a pedestrian. Unless it's Usain Bolt, who is very fast, but I don't think he could run as fast as 50 miles per hour. Nevertheless, there are all kinds of attributes that you can gather about these objects and associate with these objects as they're detected from these different sensors. So, again, what is fusion? At the top of the episode, I mentioned what fusion was in a nutshell. Let's talk about it with a little bit more depth here. Fusion is now taking these different objects that were detected from different sensors and determining, are these two objects that I detected from these two different sensors, for example, the same object or are they different? And if they're the same, I'm going to take the information, the attributes that I collected from each sensor for each object and fuse them together and say that that's really the same object. And so that's one way that you can think of fusion, but fusion really applies to fusion of the information collected from all the different sensors into a common sort of pool of objects that represent all of the objects that may be around the vehicle that the vehicle needs to be aware of for obstacle avoidance and detection, or just slowing down, pacing behind cars, whatever the appropriate response is, which is a whole other topic. But suffice it to say, before you can even get to that point, you have to fuse the information collected from all these different sensors so that you know what you're dealing with and what you actually need to avoid, what may be noise in the environment, or what's yea verily an actual object that you have to be aware of and respond to, have the vehicle stop for it or pace behind it or react in some appropriate fashion. So fusion is the collection of all this data from different sensors and making sense of what's really out there and what's not. Now, there's different types of fusion algorithms, and just talk about two broad classes here. One is temporal fusion, another is spatial fusion. At least this is how I like to think of it. And temporal fusion applies to, say, maybe a singular sensor that you have. Let's take, for example, a LiDAR. And it's going to, at time t0, give you a scan of information that was out in the environment. And from that, you can say, these are all the objects that I think are in the environment from just that singular sort of scan and this 3D point cloud that I got from this one scan of the LiDAR. And so now you have information from time t0 as to what's out there. Now, some of that may be noisy information. It might not be real. They might be ghost images due to rain or other sort of imperfections in the ability to detect what's out there in the environment, or they may be real objects. And so at the next scan of the LiDAR, you're going to get another flash or another image point cloud collection from what's in the environment to tell you, okay, now here's what's in the environment at time t1 with the next time step. And what you can do with temporal fusion is compare what you saw in time t at time t1 with what you saw in the previous cycle, time t0, and make sense that, oh, yes, this is an object. I can build confidence in the fact that what I saw at time t0 is now seen at time t1, roughly co-located, and that is certainly an object I need to be aware of. And of course, as you see that over successive time scans, time t2, 3, if it's not moving and it's in the same position, you're pretty damn sure, or you're going to increase your confidence that that's an object I should be aware of. And you're going to collect attributes about that over these different time cycles, as we'll see, merge those, and maybe refine your impression of what that object is and improve upon the information that you've gathered for that object as you see it over successive time periods. So that's really, in a nutshell, temporal fusion, right? From a singular sensor, I'm going to scan the environment. I'm going to collect targets or objects, perceive them, I should say, and determine over successive time periods that these are actually, that this is actually the same object. It may be a moving object, and therefore, if you're able to infer that over successive time periods, that these objects, this was the same object at time t1 as you saw at time t0, even though it's in a different location, you can calculate the change in distance over change in time in a particular direction, and therefore get the speed and the heading trajectory of that object as well. So that's temporal fusion, just looking at objects successively over time from maybe a single sensor. Now, spatial fusion is with all of the sensors that you have on your vehicle. You're not going to just typically have one LiDAR or one radar, depending on the application. You may have multiple LiDAR sensors positioned and mounted on the vehicle, certainly multiple radar units, and or diverse redundancy radar and LiDAR. And what you want to do is, because these sensors are mounted on different locations on the vehicle, you're going to resolve where that object is to some reference frame, maybe the reference frame of the vehicle or the georeference frame of the world, some GPS coordinates, for example, and say, okay, this sensor on the left side of the vehicle sees an object out directly in front of me about 10 meters, and this object on the right side of the vehicle, this sensor on the right side of the vehicle sees an object directly in front of me 10 meters out. That's the same object. Both sensors saw the same thing at roughly the same time, at roughly the same distance, and at roughly the same relative heading to the vehicle, and therefore it must be the same object. So spatial fusion is just that. You're taking the data from different sensors around the vehicle and formulating information that tells you whether or not these objects are the same based on these different positional locations of the sensors on the vehicle. And another thing that you might do with your fusion algorithms is kind of group the data collected from these different sensors. So, for example, if you want to first use all the data from your LiDAR sensors because they tend to produce the same types of attributes, or use all the data from your radar sensors. That's something that you might do first. You might group the sensors in that respect and create a fusion pool of objects associated with this particular type of sensor, and say, these are my LiDAR objects that I detected in some 360-degree fashion all around the vehicle, or however your LiDAR sensors are positioned on the vehicle, to tell you that here's a pool of objects that the LiDAR detected, or here's a pool of objects that the radar detected. You might also group the LiDAR based on where they're physically located on the vehicle. If you just have forward collision avoidance and then rearward collision detections, you might group these sensors based on the fact that these are the sensors looking directly in front of the vehicle, and therefore I'm going to fuse these objects in this object pool from the radar and the LiDAR that are pointing forward, and similarly on the radar and the LiDAR pointing behind the vehicle, and group the vehicles in sort of regional respects with respect to the vehicle and in that regards. So there's different ways, of course, that you can group the objects, the pools of objects collected from these different sensors. And you may not do any grouping at all aside from just the entire fusion of objects collected from all the sensors around the vehicle with your vehicle fusion pool. And typically, with any autonomous vehicle application, you're going to have at the end of the day, or at the end of the, I should say, the sensing cycles that you're operating with, this collection of objects that all of the sensors, the radar, the LiDAR, the camera, um, and other sensors, data that may have come in from the cloud or from other vehicles that tells you here's the collection of vehicles all around the vehicle in some 360-degree fashion in this sort of global with respect to the vehicle pool of objects that tell me what I should be concerned with as I now progress towards reacting to these objects and invoking different maneuvers and behaviors to deal with these objects that are around the vehicle. So that's the vehicle fusion pool. It's the collection of all the physical objects around the vehicle. And if you have a fleet management type application where you're managing fleets of autonomous vehicles or fleets of connected vehicles that have sensors on them, you may be able to share the information collected from different vehicles, or you may have sensors in the physical environment that tell you, for example, a sensor on a traffic light pole that tells you the cars that are, kind of coming into that intersection. That information may be collected and communicated to the vehicles as if they were sensors on the vehicles, but they're these sensors in the environment that provide a different perspective that the vehicle, of course, at that moment cannot possibly have, that tells the vehicle where things are in the environment so that it can be aware of them as it approaches that intersection or approaches this sort of blind zone that it can't see, and it can know in advance that there's something out there because a sensor in the environment or a sensor from another vehicle um, is telling this autonomous vehicle what's out there. And so it can you can build this fusion of objects, not just within the vehicle, but there can be a cloud-based pool of objects that represents the collection of objects that all the different connected vehicles that happen to be cooperating in that particular region or zone of operation are aware of. You can think of a mining application where this could be important with different mining trucks that are communicating what's going on in the environment, but certainly as or at an airport, certainly in campuses, geofenced applications where there's fleets of similar vehicles, um, robotaxi applications where from the same make and manufacturer, the same company may share information. So there's all kinds of ways that this can actually become a reality for improving the autonomy or the ability to detect what's out there in a more robust fashion based on the information coming in from different vehicles. Now, the latency of this detection from the cloud is going to be obviously a lot slower than what you can get from the sensors that are mounted directly on your vehicle. So if you obviously have to react in an emergency fashion, you're going to be relying on and you're going to need sensors that are on your vehicle. You can't just typically rely on the cloud unless the vehicles are operating really slow and in some sort of controlled fashion. So, but there is that concept of cloud-based fusion pools where you have that collection of objects that can be shared amongst the vehicles under control. Now, with any sort of fusion algorithm, you at some point have to, when you're looking at two objects, you have to compare them to know if they're the same object. And there's some typical rules and algorithms that can apply here. One may be are they roughly co-located, right? If they're in the same exact location, plus or minus a foot, you might assume that they're going to be the same object. You might look at the shape and the width of the width of the object that you're detecting, and if they're roughly the same shape, um, then they're also the same. But if there's two thin objects and they're spaced, say you have two objects that are about a foot wide and they're spaced a meter apart, well, maybe those are two different objects. But if you have two 2 meter objects and they're about a meter apart, well, maybe that's the same object. So there's different rules that will apply to the comparison of any two objects that you've detected to know whether or not they're the same object. And it's not just comparing against two objects that you detect at, say, time t0, but you may also be comparing objects that you've detected at time t1 to objects that you detected in time t0. And those might be have different rules because now there might have been a change in location if that object that was in the pool at time t0 has moved a little bit. And so now at time t1, you may have built up different um, uh, rules and algorithms to make an assessment as to whether or not that object is moving and the trajectory of the object, and assign confidences and build up information over time that tells you whether or not these two things are the same object. You may also determine that at, say at time t1 that, hey, this is the same object, but then at time t2 you get a little bit more information. You say, hey, what I thought was the same object are actually two different objects. It's clearer now that these are two different objects. So it's a dynamic process, right? This comparison of the information and whatever attributes you can collect from the sensors for each object to make that assessment as to, are these two things the same or are they different? So that's an important thing. And then once you determine the two objects are the same, you're going to want to merge the attributes from those two, or maybe again, multiple. I'm saying two here, but you may have three different sensors that have detected the same object. And so you may have a LiDAR on the left side of the vehicle, a LiDAR on the right side of the vehicle, and a radar right in front, and they all detect the same object. So the left LiDAR might say, hey, this object is 3 feet wide. The right object may have a different angle on it and say, hey, it's actually about 4 feet wide. And the radar up front doesn't know the width, but it knows the speed of the object, right? So what you may do in this case is say, okay, the left LiDAR and the right LiDAR both said they're the same object. I'm going to take maybe the average of those widths, or maybe my rule is I'm going to take the widest width or keep both, right? Now, what's my min and max so that I can make an assessment over time as to actually how big this vehicle is, or maybe the shape of the object that I've detected. And then the radar may give you immediate speed information about the object. So you're able to then associate and merge that attribute with this sort of fused representation of the object from all three sensors. Now, over time, too, the different LiDAR may be able to start to infer speed as well. And maybe that's more accurate than what the radar is giving you. So you may refine the speed attribute over time, but you're going to be merging the attributes from these different sensors at any particular time. And over time, you're going to evolve what these attributes, such as speed and the shape, the width, the height, and what have you, of the object is based on your successive scans and detections of that object in the environment. And then at some point, there's going to be objects that are just no more. You have to cull them from the pool because you've detected an object and it was there for about 10 cycles of scans, but now all of a sudden it's disappeared because you've moved along, or it's moved along and it's moved out of your field of view. And at some point, you might say, hey, okay, transition it from here's an object that I can actively see to, okay, here's an object that is out of sight, but it was last seen here. And then eventually, so that you don't just have a memory leak, as we like to refer to it, and have just a collection of objects that are no longer relevant to you because you're now a mile down the road and that object is far out of view. You're going to just cull it from the pool completely, certainly before that mile, perhaps. But you may cull it from the pool because it's now something that you just don't have to be worried about. It's something that happened in the past, and you don't have to be worried about. Or you save it, you persist it to disk if you think it was or to some, I should say, storage mechanism because you think it's a fixed object that you might want to be interested in responding to if you come back around to the same location later on. So that's kind of related to stale objects, and I really just kind of commented on that. But stale objects are those that you just completely remove from the pool because they're no longer seen or they're no longer relevant, and you want to kind of clean up your fusion pool of objects against which you're going to react and against which you're going to trigger behavioral responses to deal with these objects that are in your environment. So I hinted about this along the way, but there's this concept of confidence where if you see an object once, you may be you may be confident that it's kind of out there, but if you see it twice, you're going to be more confident. If you see it 3 times, you're going to increase your confidence level that that's, yea, verily, an object in the environment that I have to be concerned with. Also, it may be based on sensor information. If you see an object out at a distance, a great distance, versus something up close, you may be more confident in what you saw up close than out at a distance, and it may also depend on the sensor. If you see an object out at a great distance and it comes from the LiDAR, you may be less confident in that than if you saw it from the radar, because radar tends to have greater range and capability of being able to see things. But also, if you see something from a radar, because a radar is less precise than LiDAR, you might have a lower confidence just because it came from the radar out at some distance, because that could be picking up some metallic object or something out in the distance that is not quite something that you should be concerned with. Or maybe it detected a car, but it's in lanes three over from where you're really going to be headed, and it's not really of concern. So your confidence level may be a little bit lower, and of course, as you may have high confidence in an object that you've detected. A pedestrian crosses your path, and you have high confidence because you saw that pedestrian 50 times to 100 times as the pedestrian passed in front of you. But then as it goes out of field of view, your confidence that pedestrian is there, you may just decrease that confidence level. And then once it reaches a certain low level, remove it from the pool of objects, as we discussed earlier. So the confidence associated with an object that tells you that really is an object, it's something that you need to deal with, is going to be a dynamic variable that's going to change with how often you see it, how far out you see it, whether other rules trigger the fact that it's gone out of the field of view or whatnot. So it's an important parameter because it can actually affect, it can actually be used to affect the maneuvers. If you see an object out there at a distance and your confidence is low, you may not sort of stop immediately for it because you don't want to have a bunch of herky-jerky maneuvers with your autonomous vehicle, but you may start to slow down the vehicle such that it can be aware that, hey, there's something out there, and I'm going to wait until I get a little closer to it to make an assessment as to, yes, that's absolutely an object or not. So confidence can affect your maneuvers and how you react to these objects that are in your fused object pool. So that really, in a nutshell, is object fusion. How do we look at objects that are perceived from different sensors at different times. How do we compare them to know if they're the same object or different object? How do we merge the attributes of these objects? Um, how do we build confidence or lower confidence that these objects are something that we should consider in our maneuvers or no longer consider in our maneuvers and our reactions to avoid them or pace behind them or interact with them in some way, depending on the application. So that's Object Fusion. Hope you enjoyed this episode. See you next time. I hope you enjoyed the show Driven with me, Paul Perrone, your host. Don't forget to check us out at driven.show on the web and give us a thumbs up or subscribe here if you like the show. Thank you for listening in. See you soon.